About myself, I'm Abhishek. I think they gave the introduction about myself. I graduated from IIT Kharagpur 2013 computer science. Worked in Facebook for around 6 years. I was primarily an engineering person. My first introduction to ML was in 2019, actually 2018, when I was working in the video stream at Facebook, and our goal was to basically figure out who is going to watch what videos, because we have to generate the encodings of the videos accordingly. Like if a video is being played in India, usually 144p, 240p embeddings used to play better in India, whereas in the Europe and the US, 720p, 1080p videos play better. That's where I first got introduced to ML. ML has changed a lot since I started working on it. And to be honest, I'm really excited about the LLMs thing that has come up now. It is one of the most revolutionary technologies that has happened in our time. And we should all be really feeling really lucky that we are here to witness this change, because it is going to bring about so many opportunities that will be unlocked in the future. And we have that opportunity to bring about that change in the world. So I would highly encourage all of you to basically delve into this technology. I'll try to shed some light on it as much as I can, whatever I've learned on it, share with you some of my knowledge, and then let's go ahead. The clicker, can I get? There is no clicker here. By the way, I think like in 3-4 years, there might be an LLM giving this talk instead of me, and that day is not far. So, cool. So in this talk, we are primarily going to talk about 3 things. I'll give you a very, very high-level introduction of what are LLMs, just some basic concepts of it that will help you understand when you're trying to apply to them. We're not going to go too much into the theory. How do we use LLMs? There are primarily 3 ways that I know, and I think in the future there are more ways that are going to come up. Like one is prompt engineering. RAG, I think you all witnessed an excellent session on RAG just before this one. I'm going to go into a little bit more high level of RAG, not into the code level, and then fine-tuning of LLMs. And then we will explore the cost dynamics of LLMs. Like, there's so much talk around it, whether it makes sense to use it, how much are you going to incur, because at the end of the day, any business trying to use LLM will evaluate the ROI on using LLMs. And LLM is not a cheap technology to use. It is an expensive technology. So what are LLMs? So LLMs are basically, it's a kind of generative AI that can understand and generate English or any other language like never before. Machines have started to understand English language like we do, and this has unlocked a lot of other possibilities. There are still quirks around it, and those will be ironed over time, but this has become possible to a large extent. And fundamentally what LLMs do is basically you just say a prompt like, I love eating, and then after that, LLMs will try to find a good way to autocomplete that sentence. So it can predict like, I love eating bagels with cream cheese, my mother's meatloaf, and these things. So fundamentally, it's along those lines. Like, you give it a partial sentence or a paragraph, and it'll try to predict the next out of it. And that's why when you type in ChatGPT, it tries to autocomplete what you've already told it. So fundamentally, I just want to delve into this fact because it's kind of interesting. LLMs are based on the transformers architecture that was invented by Google in 2017. One of the fundamental things that transformers brought about was this understanding. If you see the sentence, the 2 sentences, the dog chewed the bone because it was hungry. In this case, the it refers to the dog. In the second sentence, the dog chewed the bone because it was delicious. The it refers to the bone. This understanding this is what kind of transformers enabled, that you can look at the sentence, the model can look at the sentence, and it can understand the context, that it refers to what. Like, what is this word related to in the other parts of the context that you have given it? And this was one of the primary unlocking factors that enabled LLMs to understand language the way they do. So this is kind of interesting. Like, you should understand that this is how LLMs are trying to understand what you're telling them. They just have this context thing, they're seeing the whole context, and then they're trying to relate like which word is relevant to what things are close together, what things are not close together. And this concept is called self-attention, by the way. There was a very famous paper like "Attention is All You Need" by Google, and that's where the concept comes from. What LLMs do is primarily, like, you might be wondering, how do they generate text? What LLMs primarily do is they just, as I said earlier, they just predict the next word. So if your sentence is "Financial Times is," what LLM is doing, it has a list of all the words, let's say, in the English dictionary. It is just saying which word has the highest probability that I can place after this, which will kind of make sense. And where is it getting this probability? It's getting this probability from all the data it has found on the internet, and it has probably seen this line. So this way the LLMs are trained is like you basically take all the data from the internet. You can think of it like that: every blog, every Wikipedia, whatever you can find, and just feed it to the LLM. So it has just learned those patterns. It has probably seen this word, the Financial Times, it's hundreds of times when you scout over the internet. And it's just trying to see like which word will kind of make sense after this. So you can do something like, and that's how it keeps generating the sentence. So what it will do is, the Financial Times, let's say about has the highest probability. So it will put about. Then it will have the sentence, the Financial Times is about. Then what is the word that is the highest probability? So you can keep putting the word that makes sense with the highest probability one after the other. But you can imagine if you do like this, the sentence can go in a very weird direction. Like if you just choose the highest probability word and just keep placing it. This approach is basically called a greedy approach, where you're just taking the next word and putting it next to each other. Because if you just follow that technique, it's like if you have read like greedy algorithms and all, they are greedy by definition, and they don't do like if you go a little bit ahead, they won't do a good job for you. So you can think of, this is not what happens in actual LLMs today, but this is more to just understand how you can avoid that greedy problem. So instead of doing one word at a time, if I could take all the permutation combination of all the next 4 words, but the number of possibilities will be very high. Just to imagine, if there are 4 words only, if you take 4 words at a time, you're getting 4 into 4 into 4 into 4. These many possibilities you have to analyze and then figure out which one has the highest probability of doing it. This concept is called beam search. This is not what happens today, like in many LLMs, because this is computationally very expensive. But this can help you explain, like, help you understand, like, what is the algorithm that is going underneath that is allowing the LLMs to generate. This is just basic, like, I mean, you have a base LLM that tries to auto-predict, then they auto-complete the sentence. Like, LLMs are just a very, very sophisticated auto-complete tool. That's what you can treat it like as, for your understanding purpose. You can always tune the LLM that is kind of like tuned to reply to questions. Like you can have instruction-tuned LLM, like what is the capital of France, and it will try to answer you like it is answering a person. I want to talk about tokens a little bit, because this is something, if you're starting to work with LLMs, this is something that will become extremely important. So token is like the fundamental currency of the language that LLM understands. For us, probably that fundamental currency is a character, because we understand A, B, C, D, E, F, and then you compose on top of that. There is nothing lower than a character for us. For LLMs, that is a token. And there is no one-to-one correlation between a token and something in English language that I can tell that it is equal to a word, or it is equal to a character, or it is equal to a space. There is nothing that I can tell you, but for example, in this case, if you see this sentence, learning new things is fun. Learning is 1 token for the model. Space and new is 1 token. Space and things is 1 token. Space and is 1 token. Fun is 1 token, and exclamation mark is 1 token. So this is what the model is treating as a token. Every LLM that you will work with will have a concept of context window. What it means is an LLM can only deal with few number of tokens at a time. So, and it usually is the sum of input tokens and output tokens. So, like if I'm giving a prompt to an LLM, which is like, let's say 2,000 tokens, the model only has space of 2,000 tokens left if it is a 4,000 context length model. So whenever you're working with LLMs, any LLM, like you should try to see what is the context window of that LLM, because otherwise you start getting errors like context window exceeded and things like that. Different models have different things, different context windows. You have like GPT-3, it was 2048, I think now it is 4096. GPT-4 has 16K context window also. Different LLMs have, open source LLMs have 4K, 8K context window. And if you want a rough estimate of, like I told you, there is no relationship between English language and number of tokens. But for your actual, when you're actually working with LLMs, you want a rough estimate, right? Because you only have English word. You're not going to go and every time ask how many tokens it is for the language. For a rough estimate, you can imagine 4 characters is equals to 1 token. This is on average across the English language. We have found that it roughly holds up for any blob of text. 4 characters equals to 1 token, or number of words, 3/4 of a word is equal to 1 token. So this will help you like quickly, like especially in drag and all, when you start doing things, this will become really handy, this mathematics. This is just a brief history of LLMs. I think all of us have tried out ChatGPT console and everything. This graph is not updated. It's only till June. A lot of models have come up after June also. But roughly, if you see, like, as I mentioned, transformers came up in 2017. GPT-2 came up in 2019. GPT-3 was June 2020. After that, like, a lot of models have come up. I think you know all of them pretty much. Nothing special, like open source Llama came up. And then Llama 2 came up, like, I think 2 months back, which was one of the big things in the open source world. So now let's jump into LLM applications. We'll go over the 3 things that I mentioned, prompt engineering, RAG, and fine-tuning. So prompt engineering, like, why is it even called engineering? Isn't it like just the way to talk to a model, like how you talk to a person? But there is more science to it. It is engineering because it is non-deterministic, and I'll show you a few examples of why this thing is, it deserves the attention that it commands, basically. So basically, a prompt is roughly will comprise of these 4 things, and any good prompt will have more than one or two of these components. Like instructions, you will give an instruction. I'll go over an example also. But instructions, you are telling the model what it is supposed to do. External information is you are providing context to the model, like, okay, this is the information on which you are supposed to do things. User input is the query from the user, like you are asking the model, and output indicator sets the generated text. So I think this will become much easier using this example. So this is the question, this is the prompt that I'm giving to the user, this is the instruction. The first part of this is the whole prompt, and the first part is the instruction. I'm telling the model that you have to answer based on the context that is given to you below. If you don't know the answer, just tell I don't know. Otherwise, the model will craft an answer and make sure it gives it to you. The context is the information that I'm giving to the model. The question is the question that I'm asking to the model, basically. And the reason I wrote the answer here is the output indicator. Okay. So I'm telling the model, remember that I told the model is an autocomplete tool. So when it sees an answer colon, it knows that I have to start the answer from here. If the question was something along the lines like generate Python code to do this, a good starting point would be an import statement. Because usually Python code starts from an import statement, and you could have just written import here, and the model knows that, okay, I have to start auto-completing this import statement and then complete the whole code after this. Back to the point why prompt engineering is important. Because your small differences in the way you ask the question to the model can have massive differences. And this is why we call prompt engineering. Like, just an example I'll give you. If you just ask this prompt to the model, like, what is 965 into 580? Perfectly proper question. There is no disambiguity. If you ask me this question, I will perfectly understand that I need to give you the output of this question, right? But the model doesn't understand. It will give you a different answer almost every single time. But if you just add this sentence after this, make sure your answer is exactly correct, you start getting the right answer from the model. And this is basically you're tweaking the prompt that you're giving to the model to get the model to do what you want it to do. So this is where basically the concept of prompt engineering comes in, that you have to give things the right way. And there is no standard way that this is the right way or this is the wrong way. You just have to experiment, trial and error, and figure out what gives you the right answer. You must have heard of like zero-shot or few-shot prompting. Zero-shot prompting, it's very simple concepts, nothing very fancy. Zero-shot prompting is, I'm just giving it a blank question and I'm asking it to answer. Like 2 + 2 = 2, give me the answer. One-shot prompting is, I'm already giving it one example that 2 + 2 is equals to 4, so 3 + 3 equals to what? So you are telling the model like a little bit of more information that you are supposed to behave like this. I've given you one example, now do the next one. Few-shot prompting is you just extend the number of examples to more than one, and it becomes few-shot prompting. That is all that is there to it. There's nothing very fancy about it. So not a large, but a decent number of tasks that you want to do can be done using prompt engineering itself. There are more techniques like RAG and fine-tuning we'll go into, but prompt engineering will take you a decent way ahead in the things that you're trying to do. And I'll show you one or two examples of that. So very simple example, like you want to generate like this is just generating a made-up book titles along with authors and genres, and I want the model to output in a JSON format. So this is the prompt I can give to the model, very simple. Generate a list of 3 made-up book titles and provide them in JSON format with the following keys. So I got this output from the model. If you want to teach an LLM that you are a certain person and you're supposed to reply like that, like a grandfather is talking to a child, there is a certain tone of like kindness and seniority that will come in the tone. So this is an example of, by the way, one-shot prompting. I have done one-shot prompting here because I told the model one example, that child is saying this, then the grandparent is saying this, then the child is saying this, and then the grandparent how it is supposed to say. So I could have just written grandparent and then put it. The performance would be a little bit low. This is example of one-shot prompting. I gave it one example and then let it continue. Format conversion, this will be useful for people who do coding. Basically, you are just converting from JSON to XML. If you have some JSON blob and you want to convert it to XML. Then you can also do like a little bit more fancy stuff. Others were simple. But let's imagine you have the Flipkart website. I want to get a list of all the, let's say, blue shirts for men with a certain size, like let's say medium, on Flipkart. And you want to build a chatbot to do this. Like your chatbot, people will ask like, what are the blue shirts available on Flipkart? And you want to give them a list. And they will ask in natural language to you. This you can do a large extent just using prompt engineering. How will you do it? Like, imagine Flipkart has an API that gets you all the products. I don't know if Flipkart actually has, but you can imagine that they have an API that will give you all the products, all of those things. And they have an open API spec. Like, open API spec is just describing all the APIs of Flipkart. So they already have this spec out, which is a description of all their APIs that are out there. So you can give this all API description to ChatGPT. And you can ask this question, given this open API spec, give me a curl request to fetch some options for a men's large blue button-down shirt. So you are asking ChatGPT that given the API description, tell me what is the API I need to call. If you ask this question, ChatGPT will give you the curl request to make that thing. So you first input the open API spec and the user's question to ChatGPT, get the curl request, make the curl request from your code. When you make the curl request from your Postman or any other code, you are going to get this JSON response from Flipkart, which is the list of all the shirts. And then you can, because you don't want to give the JSON response back to the user, right? You want to give them, like, there are 4 options. One is this price, this company, something like that. So then you can ask ChatGPT that given this JSON response, convert it into text that is easy to read. So you can again go back to ChatGPT with that JSON response, and you can give this, and ChatGPT is going to give you a very nice description of what the humans can understand. So this was entirely prompt engineering you used. You first got the API spec, asked ChatGPT to convert the user's query into an API call. You made the API call, got back the JSON response. You converted the JSON response back to human-readable text. And you're able to build this chatbot like this. So the question now is, we just saw this example where we were able to do this. What if the OpenAPI spec, and let's say the model, every model, as I mentioned before, has a context length. This model has a context length of, let's say, 4,000 tokens. What if the OpenAPI spec is greater than 4,000 tokens? What if the OpenAPI spec, or any other document on which you want the model to answer questions, what if it's greater than like the context length of the window, of the model? So imagine like I have a document of multiple pages. It has 75,000 words. 75,000 words is equals to 100K tokens, because based on the math that we did earlier, 3/4 of a word is equals to 1 token. So roughly we are looking at 100K tokens. how are you going to do this thing? That's the problem statement that we have. There is a model out there from Anthropic that has 100K tokens in the context. So you can go to that model, give it the entire context of 100K tokens, and you can still get it to answer. But then the question I will ask you is, what if there are thousands of documents with 1 million token? What will you do then? There is no model out there that will give you, that has a context length of 1 million tokens. So in that case, like, how do you ask questions? How do you give that as the context and ask questions on top of it? So when you arrive at this problem, that is when you can start looking at RAG, which is retrieval augmented generation. How many of you have heard or worked with RAG before? I guess everyone in the session before has done it already. But are most of you familiar with RAG? OK, nice. Cool, we'll try to see some of the intricacies of RAG. So given that I cannot give this 1 million tokens to the model, there is no way I can give this 1 million tokens to the model. So what is the approach that we can take now? All we can do is, I know that the model is only going to take 4K tokens. There is no way I can work around with it. So the max I can do is, out of this 1 million tokens that I have in all my documents, I can try to find those 4K tokens out of those 1 million tokens that might have the answer to the question that the user is trying to ask. Does this make sense? Yes. So the goal now is, you are trying to find those 4K tokens that might have the answer. Now, how do you find those 4K tokens? Imagine we'll go into the way, how do you find those 4K tokens? Imagine you found those 4K tokens, then what you can do? You can just use the context below. This is the prompt. Use the context below to answer the question at the end. In the context, you put those 4K tokens. It will not be 4K. It will be somewhere around 3.7K. You put that context. You ask the question that the user told you. And then you basically, the model will start outputting the answer. That part is clear. If there was a way I could find 4,000 tokens, then we know what to do. So now the question is, how do you find those 4,000 tokens? So we talked about we are having 4,096 tokens. Imagine like the model context length is 4,096 tokens. You have to reserve some space for the output also. The model is going to give you an answer when you ask the question, right? And this output tokens is also included inside that 4096. So imagine I'm reserving 200 tokens for the model output. Prompt template is basically what I showed you earlier. Prompt template is this text. This is very short. This is not 100 tokens now. But imagine you can put more details, like if you don't know the answer, say I don't know, blah, blah, blah. So imagine this is 100 tokens. This whole thing itself is 100 tokens. So we spent 100 tokens in the prompt template. We have to reserve 200 tokens for the output. So the only amount of tokens that I have left is 3,700 tokens, if the model is 4096 tokens. So how do I extract the 3,700 tokens out of this 1 million tokens that I have? Now, you're not going to, like, out of these 1 million tokens, you're probably not going to extract 1 token from here, 1 token from there. You're going to extract some chunks that are contiguous portions of data from this entire big blob of data, right? So the option that you have now is, you can either do, I can do 3 chunks of 1,200 tokens each, which will give me 3,600 tokens, or I can do 10 chunks of 350 tokens each, which will give me 3,500 tokens. I'm not able to fill it completely, but just a rough number. Any idea which one should we choose? Which one? First one, anybody? First one? OK, and second one? OK, so a lot of people are raising hands for the second one. In most cases, second one is the right choice. But there are cases when the first one can be the right choice. It depends, and that is why it's very important to understand the nature of your data. What are the kind of questions you are expecting to be able to figure out this trade-off? Like, I can give you an example when the second one becoming the better choice is kind of obvious. It's intuition, like, and I'll go into an example also where the second one will make sense. First one, I'll give an example of this thing. For example, let's say you're doing RAG on policy documents, and every year there is a policy document of 2013, 2014, 2015, 2016. Most of the questions are going to be, what was the policy, what was the farmer's policy in 2016? In this case, if you take 10, so the thing is, what was the farmer's policy in 2016? If that is the question, And if you're trying to find relevant chunks of farmers policy in 2016, farmers policy will be there in every single year. So you are going to pick up chunks from 2017, 18, 19, 20, and all feed it to the model out of the 10 chunks that you're going to find. But probably it's not a great idea because most of 9 chunks out of 10 are useless. You are only asking for the 2016 farmers policy, right? So in that case, probably taking that whole 2016 document and sending it as a larger chunk to the model is probably more useful than doing those small chunks. So it depends on, so this is a conscious decision you should take based on the data that you have and what are the kind of questions you're expecting. So let's say we go ahead with the 10 chunks of this chunk has the answer to my question. Like, any idea? Similarity, okay. So similarity, when you said, you'll take the similarity of what to what? The query to the chunk, right? You'll take the similarity of the query to the chunk. So you will compare this, you have your query, and you will try to figure out, is this query close to chunk 1? Is the query close to chunk 2? Is this query close to chunk 3? Now, how do you define the close thing? That's the question, right? I can define close thing by seeing like the query has some words that are also in the chunk, right? That can be one similarity metric that used to be the case a few years ago. Like if you have heard of like TF-IDF and word vector count and things like that, that's what we used to do earlier, where we would just take the word and see which words are appearing in the query and this also. But that can be like, you can imagine that can be highly inaccurate because the 2 words can mean the same thing. Like there can be France and there can be Paris. Both are kind of related, but they don't match. My query has Paris and my chunk has France. So they will not match and that chunk will be thrown away, right? So that is where the question, that is where the concept of embeddings came in. Like how do you compare if 2 English sentences are similar? Because there is no, we as humans can understand that these 2 sentences mean the same, machines cannot understand that. So that's when the concept of embeddings came. The whole point of embeddings is it will convert your English sentence to a mathematical representation. And the property of that mathematical representation is that if the 2 sentences have the same meaning, they will be close to each other by some distance metric of mathematics. We'll go into the distance metric, but mathematics can have multiple different distance metrics. Like if you have 2 points, it can be the distance between the 2 points on the xy plane. If you have 2 vectors, it can be the cosine similarity of those 2 vectors. So you have to convert your English sentence into a mathematical representation, and this is what embedding models do. So I think some of you who have attended the session earlier must have seen the embedding models. So all an embedding model does is you give it an English sentence, paragraph, a chunk, you give it an English chunk, and it will output you a vector of floating point integers, which can be of different length. It can be 500, 1,000, 1,500. To be precise, OpenAI embeddings are 1,500 dimensions. In open source, you can find dimensions 1,000 and 500 also. So you are going to get a vector back of 500 dimensions. And this is all embedding models do. And then the only property between the 2 vectors is, if I take the cosine similarity of these 2 vectors, if the English sentences mean the same, then these vectors will be close to each other. So what I'm going to do is I'm going to convert the query to an embedding. So a query is also an English sentence. I'll convert it to an embedding. I'll get a vector. And then I'm going to convert all the 5,000 chunks that I said earlier also to embeddings. So I have 5,000 vectors now. I have the query vector 1. And I'm going to take the similarity of this query vector with each of the 5,000 chunks. The 10 chunks that rank the highest in terms of closeness with this query chunk become my 10 chunks that get fed to the model. Is this concept roughly clear to everyone? So the question is now, how do you compare? So I've got this vector of, let's say, 1,000 dimensions, 1,000 floating point integer for each chunk. How do you compare the distance between the query vector and this? You take the cosine similarity and think of it like the vector had 2 dimensions, xy plane. I have the query vector as x1, query point as query vector as x1, y1, and my chunk 1 as x2, y2. Anybody remembers the maths formula to compute the distance between the two? Perfect, yes. So a lot of people remember the maths, that's good. Square root of x1 minus x2 whole square plus y1 minus y2 whole square. Think of this, that now this computation I have to do, each vector is 1,000 such dimensions, and I have to do 5,000 such computations and then I have to sort the results. That's the algorithm that you're thinking of, right? For computing, like your query vector is 1,000 dimensions, your chunk 1 is 1,000 dimensions, you're doing x1 minus x2 whole square plus x2 minus y2 whole square plus x3 minus y3 whole square till x1,000 minus y1,000 whole square and then square root of that. And you're doing this 5,000 times. You could have done this yourself. You could have totally done this yourself, no need of a vector DB. You can keep this, you can do that, you'll still get the same answer. But the thing is, this computation is extremely inefficient if you try to do it like that. Your responses will be very slow. To find those 10 chunks, you will incur a lot of compute and time, which is just not worth it, and that's where vector DB comes into the picture. So vector DB, the only goal of vector DB is to make this computation really, really fast. It does not do that computation, that naive way of doing x1 minus x2 whole square and those 5,000 things. They imply more advanced techniques that allow them to do this computation in much slower time. And that is where you need a vector DB, and that's why we need a vector DB. If you don't want, you can always do this computation yourself, and you can still get away with pretty much the same results. And there are multiple vector DBs. I think we talked about now also Chroma, Milvus, Redis, Pinecone, Quadrant, VV8. I'm not going to tell which one to use. You can use whatever you want to use. Like, pretty much all of them do the job. And this is the flow of entire RAG system that you will build. So you will have your documents. You will break down the documents into different chunks. This is the part where we broke down the document into 5,000 chunks. Each of those 5,000 chunks, you will go to the embedding model, get that vector, store that vector in the vector DB. So a vector DB now has 5,000 vectors. When your user is going to make the search query, like what is there in the document or something like that, you're first going to get the embedding of that query, the vector for that query. You are going to go to the vector DB, that this is my vector for the query. Give me the 10 most closest vectors out of those 5,000 vectors. Once you're going to get the 10 closest vectors, then you are going to, corresponding to those vectors, you're going to get the actual text, the chunk in English. You get those English chunks, 10 English chunks, and then you go to the LLM with those 10 English chunks and the prompt at the top, which we showed earlier. Like, given the information below, try to answer the question. If the information is not contained, answer I don't know. You have the 10 chunks, and then you have the query of the user. You ask the LLM is going to give you an answer, and that's the answer you return back to the user. So this is the entire flow. Any questions here? Yes, go ahead. Throughout the document.
Okay.
If your answer is distributed in 10 places, and those 10 information is needed, if I just invert the question, what is the difference in the policy between 2016, 17, 18, 19, 20? If that is the question, you need the farmer's thing from all these 5 documents, right? So if you just invert the question, suddenly the 300 token starts looking better.
Okay. Thank you.
Okay. So we'll have questions time for the end, but I just want to make sure if there is any doubt in this part, because this is very important, and I want all of you to understand this flow in very details when you walk out of this session. And I'll go into the question that you asked. I'll go into a bit of this. This is the chunking strategy. And it kind of boils down to the question that I had earlier, whether you have 1200 tokens, 3 chunks, or 10 chunks, 300 tokens. Let's say this is my paragraph, okay. It's not a big one, but imagine my model context length is like really small, 10 tokens, 12 tokens, doesn't matter. So I'm breaking this whole English, like this whole paragraphs into multiple contexts, okay. And I decided to break, I'm doing a character break. Like, I think if you have used LangChain or something, there is something called character text splitter. So you are telling that I need 300 chunks. Like earlier we talked about 300 chunks. Let's imagine the example here is 10 chunks. The moment my 10 chunks is over, I'm going to cut it off. Okay. So if you see, if I chunk it, my first chunk is ending on born on. The second chunk is starting from June 28, 1971, and ending on Musk then. Okay, the third chunk is starting on went on, ending at 1.5 billion. This is the fourth chunk. So every time the color changes, it's a new chunk. Is this part very clear? So now, tell me if these are how many chunks we have? 1, 2, 3, 4, 5, 6, 7 chunks we have. Let's say I have the luxury to send only 2 chunks to the model. My question is, when was Elon Musk born? This is the document. My question is, when was Elon Musk born? Which are the chunks you will pick out of these chunks? And think of it, the vector embeddings and everything. As humans think of it, which sentence query looks similar to that? First one will go. Okay. Second, you are saying will go. First chunk will go. You are saying first and second will go. You are saying first and last will go. Okay. You are saying second one will go. Okay. So first one will go because we think born on is there and born on is there in the query. It's going to match up very nicely, right? First one is definitely going to go. Second one, think of it like, so we are also biased. Don't think that born on and then June 28 comes, because you are not seeing them together. I will place those 5 things separately. Tell me like if second one will for surely go, or it's a chance it can go or it cannot go. There's no overlap now. I've just cut the chunks and sent it like this. There's no overlap. Second one can go. Can go, but to your argument, if there was date anywhere else, if I had written this as of 20th July 2023, then by that logic, this could have also gone, right? So we don't know if second one will go, okay? Let's imagine, I'll give you the benefit of doubt. Let's say even second one goes. At that point, you are going to give them, you're not going to concatenate them together and give it to the model. This is going to go 2 separate things. Do you want the model to answer June 28, 1971 in that case, or do you want the model to answer I don't know? Which is the right answer? I don't know, right? Because you're literally taking a chance. You can see it because it appears after this, but if I were to give you those 5 things separately, you would also not be able to tell. If as humans we cannot tell, we cannot expect the model to tell. So this is the problem in chunking strategy. So you cannot just, and this is back to the question I think that was asked, where context is important. So when you're doing RAG, like, just keep in mind that you're not cutting abruptly in places where the context is getting missed out. Because even though the answer is there in the document, it's right there, you can see it. The model will not be able to tell just because you cut it off at a random point and gave it as 2 different things to the model. So there are different strategies for doing this. Like, first of all, don't keep context windows too small. Like we discussed, 10 chunks of 350 tokens. You could take that to the extreme and you'll say, I'll do 100 chunks of 35 tokens each. You start cutting random, you start giving very, very short context and you start losing the context. Try to not cut in the middle of a sentence, only at sentence, and if possible, try to do paragraph by paragraph minimum. You can also do overlapping technique, as you mentioned, that every chunk goes behind 2 chunks overlap. You don't have to cut it. You can have an overlapping factor of 10, 20 characters, just those that you capture things a little bit, right? I mean, this thing, there are multiple approaches. You can have also, in some cases, you're not able to decide whether 10 chunks of 350 is better or 3 chunks of 1200 is better. Generate both the embeddings. and make the query both places. You can also do that. Yes, there is an advantage. As I mentioned, if your question is what is the difference in the policy document from 2015 to 2020, you need those contexts from those 5. So you need at least 5 chunks, right? Minimum 5 to 10. Smaller chunks, bigger chunk size, you mean? Yeah. Smaller token limit, is there a specific? There can be, like, not below a certain point, but till 300 tokens, you should be, 300 tokens, 300 tokens is a lot of characters. You're getting 1,000 characters in one shot. So it's a decent number of characters. Don't go very low. Don't go 30 tokens and all. It will start behaving weird. This is just the production architecture of deploying RAG. Any RAG system, if you want to deploy a production architecture, I think what we did in the session below was using notebook. A notebook will not serve your production. So you will have to take that system out from the notebook and deploy it in a proper way. So to deploy it, you'll have your own document store. You'll probably have an indexer job, which takes the documents, breaks it down into chunks. When it breaks it down into chunks, it basically calls this embedding model. This can be OpenAI or any other open source embedding model. And it'll get the embeddings, it'll dump the embeddings to the vector DB. And then you have your front-end, chatbot front-end, which queries the query service. The query service basically goes to the vector DB. It first goes to the embedding model to generate the embedding of the query. You have to use the same embedding model which you used here. You cannot use different embedding model here and different embedding model here. So you will go to so that is why you have a metadata store, which stores what is the embedding model that was used. So you generate the query embedding, you go to the vector DB with the query embedding, ask it to give you the top 10 vectors. Then you go to the LLM model. The LLM model gives you the answer, and you return it back to the chatbot front end. So this is the rough architecture of how you will deploy it. This is a quick video that we had, like, basically of this entire RAG system, the architecture that I showed you. You can play around with it. You can just upload your docs and start asking questions on it. It is just for demo purpose. It's not really meant to be anything like a product. So you can just, if you just like ask a question, it will try to answer. And you can choose which LLM you want to use on the right hand. If you see the Llama 2 7B chat, it's using a Llama 2 7B chat model. You can swap it out with OpenAI, Llama 2 13B or something like that. This is the rough way of deploying it on your own cloud. Like, you can have like the cloud layers underneath. You can have Kubernetes on top of it. You will need a job deployment framework, which is your indexing job. You will need a service deployment framework, which is to deploy that query service. Then you need the LLM deployment if you're especially using open source models. If you're working in health tech or fintech, and if an OpenAI is not an option, you can still go ahead and use this using all the open source models. They do a pretty good job, and it will take you it will take you quite far in the journey. And then you can have application deployment metadata store. I'm not going to go into too much of this, but this will basically help you bring up this system in a very scalable way so that in the future, if more documents come inside the company, you don't have to build the system again and again. You'll have like multiple document sources inside your company, and you probably want to just build one system where you can feed all the documents and then search across them. So then the question is prompt engineering and RAG enough to do all use cases? We have learned 2 techniques. So let's go into this. Like, if I give this prompt to the model, how long is the US economy likely to have inflation? All models will tell you, I don't know, I cannot answer those things, right? But if you had asked a financial expert this question, somebody who is analyzing the market today, who is seeing the facts, they would probably be able to give you a little bit more, a better answer, at least a more informed answer of what factors can affect and things like that, what is the current state and everything. So why is the LLM not able to answer this question? Because it doesn't have that intelligence and the knowledge that these experts have. All the financial experts have a lot of knowledge with experience and things like that. So this is where fine-tuning can help when you want to give a bit more knowledge to the model that the model does not have. An example of this can be, so these models are trained over publicly available data. If there is some financial data that is specific to your company, that cannot be found on Google, that is data that your company owns or you have, this LLM can never be able to put that intelligence and answer you based on that. And that is when you have data whose distribution is very different than the data on which LLM was trained, fine-tuning can be effective. You can make the LLM smart like a financial expert if you can feed all the data that this financial expert is seeing from within the company. So this is where fine-tuning can help. And this is the part that I told you about, like if you can gather from all finance experts to the LLM. Regarding fine-tuning, I'll not go very deep into it. In case of fine-tuning, you'll need a bit more ML knowledge. Till prompt engineering and RAG, even engineers like with zero knowledge of ML, you can still go do that. Fine-tuning also does not require a lot of ML knowledge, but it does require some understanding. So there are two types of fine-tuning, basically unsupervised fine-tuning, in which case you have like blobs of data with you, like huge amount of data you have, and you are just giving it to the LLM, and the same way LLM was trained on the publicly available internet data, you are able to give the data in that format. This data is easy to find, and you can just give it. The other one is supervised tuning. Supervised tuning is you already have prompt completion pairs. So an LLM model is what? The input is the prompt, and the output is the completion, right? So if you already have pairs of that format, a lot of samples, like this is the prompt, this is the completion, this is the prompt, this is the completion, you can fine-tune the model with that, and then you can basically get the answers accordingly. And ChatGPT was basically, original model was like OpenAI DaVinci GPT model, and then ChatGPT is just a training on, it's called instruction tuning. It's just a fine tuning on top of the original model, where it's trained to answer questions. There are more techniques that have come up, like originally full fine tuning is a very, very expensive affair. It takes a lot of time also. But there are more advanced techniques like PEFT has come up, which is parameter efficient fine tuning. There is LoRa. So in this technique, you are not changing all the weights of the model. You are just changing the last layers, and that too, like, you basically find out a different matrix weight that you apply on the original model, and that kind of helps to tune the model to your data. So that is roughly around fine-tuning. In short, like, if you have this question, should we fine-tune or should we not fine-tune? If you have some sort of proprietary data, that is one option that fine-tuning can help you. Or if you're doing some simple task for which ChatGPT is an overkill, like for example, if you're just doing classification, like sentiment classification, whether it's a happy mood or a sad mood, you can do it using ChatGPT also, but it is just an overkill because you are paying too much for such a simple job that even a 7 billion model can do very well for you. So you're just spending much more than what you need to spend. So in that case, like what I would suggest is just take a very small model, like 7B, 1 billion model you will also take. You already have your sentence and the sentiment, you have your training data, just feed it to it, and you can get that, you can lower the latency and the cost when you put this to production. So that is when you can get this. And I think there are also studies, and we have also found that especially for certain use cases, you can actually train Llama 7B to become equal to ChatGPT for your use case, just by giving the training data. So it will perform as good as ChatGPT. So there's no point of paying that extra cost. I'll go into the economics of LLM applications. This part is very interesting because I think most people don't do this analysis and don't know about this part. So for the same task, you can spend $360,000 also, and you can probably do that task in $3,600 also. The decision, it's not about what is the right decision. It's about knowing what are the factors that help me take the right decision. So what I would ask you is to focus on the factors more than the actual cost, because there is no right answer to this. In some cases, this might be the right answer. In some cases, that might be the right answer. So it's important to understand the factors behind the two. So we'll take 3 problem statements. The 3 things that we discussed today, we are going to take 3 problem statements. We are going to summarize the whole Wikipedia to half its size, which is purely prompt engineering. This is the first use case that we discussed. I'm just going to give a prompt. This is the whole Wikipedia. Summarize it to half its thing. You might be wondering, like, whole Wikipedia is much longer than the context length. Think of it like I'm just giving it article by article. So at the end of the day, my goal is to summarize all of Wikipedia to half its size. I'm going to implement search on Wikipedia with RAG, the second thing that we discussed. And the third thing is we are going to fine-tuning and inferencing a model. I'm going to fine-tune the model on the whole Wikipedia data set, and then I'm going to ask questions on it. And we are going to compare the cost of doing it across different models. So let's go with the first, summarize Wikipedia to half its size. Wikipedia has 6 million articles. Each article around 750 words. 750 words is equals to 1,000 tokens, because 3/4 of a word is equals to 1 token. So I'm totally looking at 6 billion tokens. I have 6 billion tokens that I want to summarize it to. When I summarize it to half, I will get 3 billion token output, right? Let's say I'm planning to do this. I'm going to compare doing this task with OpenAI's GPT-4 8K context length, OpenAI's GPT-4 32K context length, GPT 3.5 Turbo, and then I'm going to take open source Llama 2 70 billion and Falcon 40 billion. We're going to do the same task across 5 of these models. With the GPT-4 8K context length, my cost of doing this will be $360,000. How do I derive this cost? So my input tokens is 6 billion, my output tokens is 3 billion, right? So that's why you see this, sorry. Yeah, so that's why you see this 6 billion input tokens, and then this is the cost per input token. So GPT-4 8K context length cost is, I think it's $3 per million tokens or something like that, $30 per million token. Okay, so this is the maths, and for the output tokens, it is $60 per million tokens. So this maths, if you do, you are going to come up to $360,000. If you do the same thing in GPT-4 context length, you're going to get $720,000. If you do the same thing in GPT 3.5, you're going to incur $15,000. So did you see the price difference? Like, we're talking about 720K, 360K, 15K. If you do the same thing on Llama 2 70 billion self-hosted, you're going to incur $14,000. If you do it on Falcon 40B self-hosted, you're going to incur $5,000. So now whether the quality is good enough for you, what is giving you good quality is worth trying. But I would try it on the order of 5,000, 15,000, 40,000 instead of going the other way around, just to save that money, at least, right? Then let's go to the next use case, which is implementing search on Wikipedia with RAG. So in the search on Wikipedia with RAG, we are going to compare 2 things. We are going to use, for the embeddings model, OpenAI embeddings, which is ADA embeddings, and the OpenAI GPT 3.5 Turbo. And on the open source land, I'm going to use E5 large V2 embedding model and Falcon 40B for inference. And in this case, so here, like, you have 2 costs. You basically have one indexing cost and one the total is your inference cost. Indexing cost is when you're first breaking it down into chunks, you're getting the embeddings, and then you're storing it. Your embedding cost is $600. Your inference cost, if you're doing 1 million queries daily basis, I'm assuming 1 million queries you're asking questions on Wikipedia, it's going to come out to be around $3,400. The same thing you do on open source model, your embedding cost is $83, and your inference cost is $1,400. So we are comparing 600 plus 3,400, and this is per daily cost, by the way. This you are going to incur every single day, the 3,400. It's not a one-time cost. This is a one-time cost. So 3,400 versus $1,400. And then I'll take the fine-tuning model cost. So if you do, here I'm going to compare OpenAI Curie model, which is a 13 billion model, versus Llama 2, 13 billion model, same models. In this case, your indexing cost is $27,000, and your daily cost, if you're making queries to this fine-tuned model, 1 million queries every single day, you're going to incur $26,400. The same thing you do on the open source land, you're going to do on Llama V2 13B, you're going to incur $1,365 one-time cost and $470 inference cost. The inference cost is highly different. If you see, like, it's orders of magnitude high, because OpenAI makes the cost of serving any fine-tuned model 10x. If your ChatGPT is like X, fine-tuned model will cost you 10x for inference. So that is roughly it from my side. Hopefully this was useful. Thank you, everyone.